Good afternoon, everyone. This is Vamshi Vijay Nakkirtha. I'm one of the senior engineering managers in AWS.
Yeah, hi everyone. My name is Navneet. I'm one of the senior software developer in AWS.
Today, we are going to talk about OpenSearch evolution to trillion-scale vector database. So let me walk you through the agenda. So we will introduce you to OpenSearch, and then introduce to some of the vector basics. And we take you through the journey of how OpenSearch evolved into a trillion-scale vector database, and what's beyond 2025, and how we made VectorDB made easy for AI application builders. So let's begin with what is OpenSearch. Most of you might already be aware of OpenSearch, but for those who are new, OpenSearch is a popular, community-driven, open-source search, analytics, and vector database platform with integrated tools for observability, security, visualization, and powered applications. OpenSearch is under Linux Foundation. We recently celebrated 1-year anniversary. And we have a very vibrant and thriving community with industry-leading partners. The best part of OpenSearch, it helps you accelerate and simplify your AI application development. With its rich vector database features, search features, it delivers you a low-latency, cost-optimized solution. And the best part of it is it has native integrations to foundation models, which makes your enterprise search smarter and better. Going to a vector, if you are building AI applications, directly or indirectly, you might be hearing this word vector for similarity search, semantic search, hybrid search, multimodal search. So it's a very core foundational block in AI applications. So let's understand what actually a vector means. So a vector is a numerical representation of your data, which captures the semantic meaning and content relationships. So given your data, it could be your image, video, audio, text. Once it's fed into an embedding model, it generates these vectors. Think of vectors as simple array of floating point numbers. Each number is a dimension, and it's 4 bytes. The number of dimensions of a vector depends on the embedding model you choose. Now moving on to vector similarity search. So when we say two vectors are similar, they share the same meaning and context. Think of vectors like a point in a multidimensional space. So we fed all the data to the embedding models, and embedding models generates these points, and these points are projected in the space, high-dimensional space. We said two vectors are similar when they are closer to each other. So the position and the orientation tells you the relationship between these objects, between these vectors. Now, to know whether two vectors are closer to each other or similar to each other, there are certain similarity functions. The popular ones are the Euclidean, where you measure by distance. The closer the distance, the better the similarity. Or cosine, you decide based on the orientation. The minimum the angle, the closer they are. And the dot product, you look at the magnitude and the direction. Now, the type of similarity function to choose depends on also your model that generated these vectors. Let's take an example. So you have a music album database. So you run your albums through the embedding model, a audio embedding model, and that will generate the vectors. And you project all those points in the space. And now you are listening to a particular song. And you want to find all the similar songs to this. So the way we do is, the song that you're listening also goes through the embedding model, gets a point out of it, which is a vector, and then you find out all the nearest points to this song in the space. Those are all the closest recommendations you can possibly get. So this is what a typical VectorDB does day in and day out. A VectorDB helps you to take these vectors, efficiently organize them in memory, on disk. When a query vector comes in, it's able to retrieve those top nearest neighbors or similar vectors and give you back. So moving on. So to explain how OpenSearch works behind the scenes, we show you a very simple example of how the indexing happens and how the search flow happens. So as part of indexing, you would put your vectors in a JSON and send a REST API call. So in OpenSearch, everything is based on JSON and the REST API. And once you send those requests, it lands on an index. Think of index as a table in a relational world. Now, this index is divided into multiple partitions, which we call as shards. And these shards are distributed across the data nodes. As you send your data, it randomly assigns the shards based on the document ID. There is some hash function. It figures out which data node to go and reside, and that's a part of indexing. And moving to the search, now when the query vector comes to the coordinator, basically coordinator is the node that receives the query from the user. It understands that, hey, this user is talking to a particular index, and this particular index shards resides in A, B, C data nodes. It routes the request, the coordinator routes those requests to those data nodes, and the data nodes locally process these requests and return back the results to coordinator. The coordinator reaggregates and sends the response back. So this is a basic search and indexing flow. Now let's talk about the journey of how OpenSearch evolved as a trillion-scale vector database. So the inception of OpenSearch vector database began in 2019. When the OpenSearch started, I think the scale is around tens of millions of vectors. And as the years progressed, the scale just grew exponentially. And the reason being, the embedding models have evolved. The innovations in embedding model has skyrocketed. Initially, the embedding models were converting images to vectors, audio to vectors. The moment the sentence transformers came into popularity, the moment the text gets converted to vector, the enterprise search took a 180-degree turn for the semantic search. That brought in more and more use cases. And now with the Gen AI boom, with the agents, the workload just kept on increasing. And now we are in a position of seeing trillions of vectors. And the best part, OpenSearch has evolved through this journey to handle these workloads and become a popular choice in the open source world. Because it started very early, much early, the Gen AI boom was in 2023, 2024. So it had this 3-4 years of early start. And as it matured, it has enough time to go through these workloads and mature, and in a matured space to get this popularity. Okay, moving on. So when we started, when the OpenSearch started vector database in 2020, the primary use case was from computer vision perspective. So there were use cases for finding the face recognition. Given a face, find the similarity face, or given an image, find similar images, or finding for a particular scene in an audio. And then as the embedding models evolved to convert vectors, to transform the audio and video files to vectors, the recommendation systems also prevailed. So then there were recommendations for product recommendations, music recommendations, video recommendations. So all these use cases were in the range of tens of millions of vectors. And at the beginning, the simple naive approach was to run a brute force search. Take a query vector, compute the distances to all the existing points, basically all the existing vectors, and then return the top k vectors. But that doesn't scale with the millions of vectors. So this was one of the challenge. So to tackle this, we integrated with an HNSW, with an industry popular algorithm called HNSW, which is hierarchical navigable small worlds. On a high level, it's an approximation algorithm. As you ingest your data, it arranges these vectors in the layers in a way, while you search, you can skip through these layers and reach to your point of interest, and then just search in that particular layer. So this brings down the latency from order of n, basically going through all the vectors to a logarithmic complexity. So you are now able to get the latencies from seconds to milliseconds. Until 2020, it was all great. And now moving to around between 2020, like late 2020s and early 2021, we saw the evolution of the NLP models like BERT, which started generating vectors for text. As we all know, with vectors, now we capture semantic meaning. So it revolutionized the text search, the enterprise text search. Originally, the text search is all about, give me the documents that match my keyword. Apple is a fruit, so it finds out all the documents that matches apple, fruit, and gives you. But what if the question is talking about eatable items, something like this? So eatable items has a context, so fruits can be eatable. So those kind of information can be the understanding of your basically vectors enables to understand the intent of the question, the context in the question, and find the relevant matches. So that revolutionized the text search, which we are recently calling it as semantic search use cases. And with this, the scale has moved from tens of millions to billion vectors, because all the text search, it could be your Wikimedia, or it could be all your internal company documents, the scale would just be in billions. And now the major challenge we faced was HNSW is very popular. Yes, it resides in memory. But to have billion vectors in memory, it's going to be a very costly affair. So to scale to these workloads, OpenSearch started looking into the quantization techniques, which help to compress these vectors in the memory. So there were two popular quantization techniques, even now, the scalar and the product quantizations. In scalar quantization, the number of dimensions remain the same, but every dimension, you project it from 4 bytes to either 2 bytes or a single byte. So OpenSearch introduced FP16, which is a 2-byte representation of float. Then there is a byte representation of float. So with that, you're able to reduce the memory footprint up to 75%. And then there's another technique, product quantization. This involves training. So if you understand your production data, if you are able to extract a sample of your production data and run through these training algorithms like IVF and PQ, you could compress the dimensions. So essentially, what we will be doing is with PQ, you're trying to take a vector and project it from a high-dimensional space to low-dimensional space. So 100-dimension vector would become a 20-dimension vector or a 10-dimension vector. So you could see a massive reduction in the memory footprint. And the memory footprint reduction was not just enough. So we said semantic search was evolving, but semantic search also had problems. Semantic search, like vectors, help you understand the content, the context, the meaning in the question. But if there are certain constants, like let's say account ID or SSN numbers, something like this, which has the constants in it, there's no semantic meaning involved there. But if you pass it through a model, it will give you some vector for it. So that's where the accuracy of the results started to drop when there are more constants in your queries, where text search performs well. If there are exact matches, text search gives you the better results. If there is like contextual information, vector search can give you better results. So that's where the community gave us this idea of developing a hybrid search, which helped to combine the benefits of both these searches, the text search as well as the vector search. So you get the results from both those, and then you merge the results and send back to the user. So you are able to improve the relevancy. And based on our benchmarks, we are able to see up to 8 to 12% of improvement in the search relevancy at NDCG 10. So we have this information in the blogs. We will show you the barcodes in the end. Please feel free to take a look at this. And then another interesting angle emerged. So now you have text, you have vectors. Then community users started sending text with filters and then vectors. There were very interesting use cases like, hey, can we do geo-based filters and then combine with vectors? Can I do aggregations with vectors? The use cases started piling up. This is where the OpenSearch shined. OpenSearch started as a search engine. We realized to be an efficient vector database, you have to be a top-notch search engine. Because as a search engine, you will be able to provide aggregations, filtering, all types of filtering, regular expression search, prefix search, and you are able to combine this with the semantic search, the hybrid search just became better and powerful. And this attracted large workloads up to billion scale, and OpenSearch is able to handle that. And then now with images and text, there's also multimodal search that evolved, and OpenSearch had an ability to perform the multimodal search through our ML connectors, which we will touch up on the next slides. It was all well going through the 2022s, and then around 2023, early 2022s, we observed there is a boom of generative AI. We all know about it, and then there is the prevalent use case of RAGs. Everybody wants to have the knowledge bases because LLMs are trained only till 2021, and then your company data or whatever your private files are latest, and LLMs are not able to understand this. So you need these knowledge bases to bridge the gap, to enrich your prompt and let LLM understand the information so it can better summarize for you. And the RAG use cases just let the workloads to move from billions to hundreds of billions. And these use cases are like powering chatbots, knowledge assistants, domain-specific AIs. And then we realized for hundreds of billions, again, the compression we are doing was up to like 4x compression with scalar. Product quantization does better, but it involves training. And not everybody understands the production data. So the product quantization is for just more like a power user kind of a tool. But majority of the community was depending on scalar quantization, which is basically it keeps the dimension same, but project your vectors, project your dimension from 4 bytes to 2 bytes, from 2 bytes to 1 byte. We realized at 4x compression as well, the cost is going to be cost is going to play a key role. So we need much better scalar quantization. So we started adding up to 32x quantization using the binary quantization. And then we realized we need to have the vectors surfaced from the disk to reduce the memory footprint. And the problem with this is, well, we are going to 32x compression. From 4 bytes, you are going to 1 bit, but there is loss of data. How do we make up for the loss of this data? Because it will hamper your results. So then OpenSearch added disk-based vector search to reduce the memory footprint. And then it added re-ranking on top of the disk-based vector search to make up for the loss in the data. So as you see on the screen, so the disk-based vector search works in a way, you build a highly compressed index. So from 4 bytes to 1 bit, it is 32x compression. So you build a highly compressed index, put it in memory, and then you put all the full precision vectors, the original vectors, on the disk. Now when the query vector comes in, you talk to the highly compressed index, and then retrieve the full precision vectors from the disk and re-rank them. So with this, you're able to preserve the accuracy. And then the search, with this scale, the search latencies are also important. So we OpenSearch started looking into the hardware acceleration. So you might be already aware of the SIMD instructions. So x86 architecture has a different level of SIMD support, and then the ARM processors have a different level of SIMD support. Essentially, these are CPU registers which help you to accelerate the vector operations, the multiplications and additions. So that also helped us to get into the millisecond latencies. And then in the recent 2025s and late 2024s, we see the AI agents evolve with the use cases of using vectors for memory, reasoning, personal assistance, and they became a core AI infrastructure. And this led to the workloads moving from hundreds of billions to even trillions. At this scale, when you have to build a vector index, like you take a billions of vectors and try to build a graph out of it, which is HNSW, it would take hours to days. Now, beyond 100 billion, it will take from days to weeks, which is practically not scalable. Because the models keep evolving, you need to regenerate the vectors, you need to reindex, it's going to become a problem. So what we understood is CPUs are not going to evolve at this scale. We need to shift to GPUs. So OpenSearch recently introduced the GPU support. And with that, we are able to see from 9.5x to around 12x improvement in the index builds. And then the CPU cost reduction in 2.5x. And then the memory, around 3.7x reduction in cost, and then 2.5x reduction in CPU utilization. Because now we are offloading to GPU, the compute power in CPU is saved, so you can scale down your CPU instances, which further reduce the cost. And then at trillion scale and hundreds of billions of scale, even the storage becomes a point of cost explosion. So OpenSearch provided a way to plug your vectors in a remote store. It's cloud native. You can pick up any of your cloud vendors, and it has an ability to offload vectors to the remote store, and then just keep the text with it. And with this, you're able to decouple the vector part from the OpenSearch cluster and still let OpenSearch talk to the remote stores and then merge and get the results for you. OK, now what's next? So the GPU-based acceleration has been made available for indexing. And we all want the searches also to be in the order of milliseconds. With trillion scales, it's going to be a challenging problem. So the next logical step is to enable GPUs for search. But the problem is, to keep these graphs in memory for GPU, it's going to be a costly affair again. So we need a way for us to efficiently utilize the GPU memory. And there are interesting RFCs on OpenSearch, GitHub. Please have a look. And then we also want, and then the next logical step is to work on the optimized disk reads, because now we introduce disk-based vector search. You're going to disk to read these vectors. If the vectors are spread across the disk, then you need multiple disk seeks. And we all know disk seeks is costly. So we're trying to arrange the vectors on the disk in a way that all the closest vectors reside closer in the disk. So with lesser disk seeks, you're able to get all the vectors you want. That would minimize the latency and also reduce the I/O throttling. And we want to look beyond 32x compression and introduce smart routing. So I was talking about the OpenSearch architecture. The coordinator will identify all the shards, and it sends requests to all the shards. But we could be smart over there and identify, using these vectors, you could identify that the closest neighbors for these vectors would just be on a subset of shards and just route to those shards. That would reduce the resource consumption and boost the throughput by 3x. And then the multi-tenancy with resource isolation. So as the vector workloads are growing, the number of applications are growing. Community wants a well isolation of resources between these tenants. So one tenant doesn't create a noisy neighbor problem to another tenant. And the OpenSearch continues to evolve its search relevancy. So we are adding the late interaction models, the maximum marginal relevance retrieval, which helps boost the vector search results. We have the barcodes. Please feel free to take the pictures, and you should be able to go through these blocks. Sorry. OK. And coming back to the OpenSearch VectorDB made easy, what we realized in the community is it's not just enough to have a trillion-scale vector database. OpenSearch is able to handle it, but it's also important to have the AI application builders easily onboard to this highly scalable system. So we need a user-friendly way to onboard the agentic applications, AI-based applications onto OpenSearch. So OpenSearch introduced these ML connectors, which help you to establish connections to your favorite models. It could be your OpenAI, your Cohere, your Bedrock. You bring us the endpoint and connect it into the OpenSearch and just index your data. Let the data flow through OpenSearch. OpenSearch handles talking to your models, getting those embeddings, and store it in the index, and provide you for the search. So you don't have to manage multiple endpoints. You just need to plug in and handle and OpenSearch handles it for you. And then what we realized is, now we have these connectors. We have the building blocks. So on OpenSearch dashboards, we introduced this concept of AI flows. Now with this concept, with this feature, without having to write any code, you can just drag and drop these components and build your whole workflow. So you can put your indexer, you can put your ingestion pipeline, then you can attach your search pipeline to the index, and then drag and drop, and then build the application end to end using the AI flows on OpenSearch dashboard. And OpenSearch also launched the agentic framework. Now you should be able to build your agent applications within OpenSearch. Some of these could be your agentic RAG, your conversational agents, etc. And OpenSearch also launched the model MCP servers, the model context protocol servers within OpenSearch, which helps your agents to communicate, to retrieve the context for its memory, either it could be memory, reasoning, in a safe and secure way using the MCP protocol. And we have another session at 2:25. One of my colleagues, Dotton, will walk you through how to build these AI applications on all the scalability factors we discussed. So he'll dive through those AI applications at 2:25. Please feel free to check out the session. And with this, we conclude the session. Thanks, everyone.
Thank you.